these kind of thing actually we simulate, and it is basically simulated in Lumerical. As you can see that this is my structure, this is my geometry, and which is dimension is typically a 20 micron. And let's say for example, if I use operating wavelength, I'm using two different operating wavelengths. One is zero point 0.4 micron and one is 4 micron. You know that zero point 0.4 micron is typically small, pretty small compared to the 20 micron. As you can see that when the light is coming, the EM energy is coming, and it simply interacts with the surfaces, and you know it simply goes back, simply completely reflects from the surfaces. So it's a one typical phenomenon. Of course we know it's as a reflection, but what will happen is when the geometry is comparable with the with the wavelength of the light. Okay, so it's a one simple example. So as you can see that this is, I'm sorry, as you can see that this is at 20 micron. Okay, that's why I've used a 4 micron. And you can see that when I'm using this particular wavelength, and you see that apart from the reflection also we have interference and diffraction as well. Okay, so basically the simulation actually simulating those effect as well. Okay, whereas if the geometry is very big, the simulation actually simply neglects those behavior, those phenomena. Okay, but that's what, but in photonic simulations, it really happens. Okay, because our structure is not very much big compared to the geometry, compared to the wavelength of light. It's comparable to the wavelength or even lesser, or it could be a sub-wavelength structure. Okay, just like a metamaterials. So that's why we need to also understand about the interference effect and the diffraction effects when it when the light interacts with the matter, or let's say, or the device. Okay, so now coming to the solver. Yes, I was talking about the stability earlier. So these are the typical application part. I can uh, uh, yeah, I can explain. So basically, uh, I talk about I will talk about, of course, the solar cell part. But this is one type of applications. But yeah, so these are some applications. For example, nanoparticle scattering for diffusive surface designing. Or let's say for example metamaterials. I was talking about the metamaterials since beginning. So the metamaterials also we yeah, so the metamaterials I was explaining that we can design the meta lens. You know, Meta lens is, of course, is right now it's a very hot topic. People are also trying to get rid of the bulk conventional lenses, and it can be replaced by the meta lens as well. And see, if you see the each and every pillars. Okay, is basically it is a term. The size is in terms of micron. Okay, the height of the unit cells, or the dimension of the unit cells, right? Uh, so understand about the meta lens, we need to, first of all, we need to understand the property of the property of the each and every pillars, how it actually bends light, how it introduces the phase between 0 to 2 pi. That we need to understand. We need to optimize the pillar size. Those things we can do, and then we come up with the overall lens material. Okay. uh, yeah, so for this example, if you look at this particular image, this metal lens image, it's a quite big structure. Actually, it's around 10 to 25 millimeter diameter. And as I mentioned, the 10 to 25 millimeter diameter simulations in numerical in FDTD takes a lot of time. And that's why we need this high performance computing. Specifically, this high performance computing is mostly used for this metal lens simulations. Okay, these are very big. And yeah, and that's the reason. Now coming to the diffractive optics, yes, CMOS sensors, very efficiently we can simulate the CMOS sensors. We can understand about the crosstalks, we can understand about the quantum efficiency. Uh, uh, anyway, this kind of a quantum efficiency is you can relate with the solar cell as well. I'll come to that point. Then we can definitely use a grating coupler. We can design the grating coupler for combining the light from fiber to waveguides. That is also possible. And one major advantage of this particular tool is we can do the inverse design automations. Okay, it is compatible with Python. And the inverse design is something, okay, in that case, where you can define the objective basically. Okay, what kind of physical parameter you are looking for, and based on the physical parameters what you are looking for, based on that, uh, your device will be created. Okay, it's completely inverse. And this is a very powerful thing, very unique thing which actually Lumerical gives. Now coming to this RCWA stack, yes, RCWA it's a basically a semi-analytical method which actually solve the Maxwell's equation in frequency domain, whereas FDTD solve in the time domain. So you know that if you discretize if you discrete the time domain, if you make it smaller. More time will take to simulate, but in the RCWA actually we do it in the Fourier. We make it as a time independent simulation, time independent algorithm, and that's why it is pretty faster compared to FDTD. The application mostly is in the diffractive optics simulations, okay, photonic crystal simulations, and also we have the stack, which is basically useful for the thin film simulations, coatings, anti-reflection coating. Anyway, because when you design the solar cell, you need to put the anti-reflection coating on the top of the active layer just to minimize the reflections. So in that case also we need to understand about the which kind of what should be the thin film thickness, okay, to get the to get the destructive interference, so that we can get the very low reflection, okay, from the surface, okay. That's why we need this stack solver to understand about the thin film structure, thin film coatings. Now Lumerical mode. In Lumerical mode, I was talking about this waveguide. As I was talking about this waveguide, this algorithm, basically it actually calculates the mode profile of a certain waveguide. It comes with the three different solvers. One is called a finite difference eigenmode, one is called the eigenmode expansion solver, and one is called a variability. Okay. So eigenmode expansion, I need to explain a bit. Maybe tomorrow I will do it, because tomorrow I will mostly focus on this particular mode solver. Okay, how the mode solver actually works for the waveguide. So I'll keep it aside for tomorrow. Yeah, the solution in the multiphysics environment. Yes, I was talking about the chart solver and hit solver. So in the chart solver, actually it needs for designing active components. It could be modulators, or it could be photodiode, or it could be solar cell as well, photovoltaic cell as well. Okay, wherever ultimately in solar cell we actually collect the charges. So that is our uh, final target. Okay, so how efficiently we can collect the charges, okay, and what happens, okay, when at the junction, at the middle junction, at the middle dielectric junction, okay, because these kind of junctions actually uh, it changes the if I talk about the photovoltaic cell, it actually changes the open circuit voltage or the short circuit current, okay. uh, so that's why how efficiently effectively we can design it so that we can minimize those, we can so basically we can increase the short circuit current, and also the open circuit voltage. So these things are very crucial for designing solar cells, and those kind of answers can be only can only the chart solver give you. Okay. Now coming to the heat solver, the heat solvers we actually basically talks about the thermal management of certain uh, component, for example solar cell, how the heat is being distributed, because if it is too much, if the solar cell is getting heated too much, the active layers, for example the semiconductor inorganic materials, okay, it might shift the energy level, okay, because of that it's their band gap shifted, and of course eventually it will lead to a lot of problems. Okay, so you need to understand about the heat distribution as well, and that heat solver we can do. In the multi-quantum Gale solver, we actually use it for for designing quantum well. Okay, uh, uh, just to understand about the charge density of a quantum well of a superlattice structures, which it's a bit different compared to a simple bandgap structure, normal bulk material. Okay, the electrostatic potential, and how the electrostatic potentials, how if you apply the voltage, how the energy band shifted. Okay, and because of the shifting, okay, because of the shifting, it leads you it changes the absorption peak. Okay, the excitonic absorption peak, it shifted because of the application of the voltages, right? So these things actually we understand in the QWN solver. Okay, it's basically a part of the part of multiphysics solvers. Yeah, so just quickly just go through this through the application part. That is, we have the DGTD. Basically DGTD is a counterpart of FDTD, which stands for that is continuous Galerkin time domain method. It is mostly useful when you design some complicated structure, some structure. For example, the some sphere, some sphere. Let's say particle. Okay, let's say the you put the particle on the top of a substrate. Okay, and it creates some dielectric metal interfaces. Okay, wherever the sphere touches with the dielectric. Okay, so in that case, if you're designing a, if you are designing a plasmonic material, plasmonic, if you want to understand about the plasmonic nature of this particular particle, and how the electric field getting enhanced at the interfaces, the dielectric interfaces. So in that cases, if I talk about in terms of simulations, okay, in that case, and those structures is very minute, very small in dimension. Okay, basically in terms of nanometer. uh, and in that cases, you need a very fine meshes at the interfaces. Okay, so that it can resolve the electric field and the magnetic field at the interfaces. Okay, so that's why we need this DGTD. And this DGTD actually comes with this unstructured mesh. That is the power of the DGTD. We call it as a finite element analysis in Lumerical. Lumerical also provides this kind of analysis, as you can see in my slide. So I was talking about that particular example, so you can witness it from here. So this is how actually the meshing happens. Okay, and also it has the property to adapt the to do the adaptive meshing. Okay, okay, so that's also we do in DGTD. Then we have the finite element eigen mode method. It's a counterpart of mode FDE solver, where actually we use this finite element analysis, the advantage, the power of FEA, just to understand about the modal property of a waveguide. Okay. Okay, last but not the least is the photonic integrated circuit. I was talking about this thing earlier. So it's basically a system level simulation tool. It can perform the frequency and the time domain simulations for various uh, for designing various of optical system. Okay, for example, if you want to design a WDM multiplexes, okay, you need this circuit level simulation tool, because a particular WDM circuit solver, it consists of different optical components. Okay, it has sources, it has splitters, it has filters, optical filters. Okay, it has detectors. So all these things are combined together, and just to check the overall circuit simulation, how actually the circuit behaves. Anyway, so tomorrow also I'm going to spend some times on the on circuit solver, how we actually simulate, how we can use it for designing communication circuit. Okay, which can be useful for communication. uh, then yeah so Lumerical actually support different foundries. As you know, that foundries is very much helpful for fabrication. This actually so basically, these are not typical type of foundry partners are currently closely working with Ansys Lumerical. Uh, uh, each and every partners, it actually provides a various material platform. For example, silicon foundries provide the silicon foundry informations, indium phosphide foundry, silicon nitride foundries, all are separate, and it has different all the foundries have different applications, of course, in numerical. So I was talking about it's a combination of optical and the multiphysics simulations. As you can see that we actually, let's say for example, if I design a certain waveguide and we launch the light, okay, and how we see that how the light can be split it from the junctions, and it could be splitted equally, or it could be splitted 75% 25% ratio as well. uh, so this is a one part where actually we have designed a silicon on insulator waveguide. We can simulate electro-optical modulators, right? uh, by part we actually use this tool, because if you look at a certain component, a certain, let's say, electro-optical modulator, so it has the optical part as well as the electrical part, right? So the optical part actually we have FDTD mode, and so on. So these tools actually we use to understand about the optical behavior, and the electrical simulations we do understand about the charge property, the charge behavior, basically. And these are dynamic, these are link these are completely work together, seamlessly work together. So these are some definite workflow. Definitely, maybe someday I'll work on active devices, and maybe I can give you a demo on that.